So welcome back to High Performance Computing, Advanced Scientific Computing, our lecture 0, Prologue, the second part. In this first part, we basically have an idea of HPC already conveyed to you. Of course, there will be more lectures having much more information about it, but you should have first glimpses on how basically the high performance computers will be, what topics are related to it. We have seen architectures of different CPUs versus GPUs. We have seen distributed memory and shared memory roughly, but of course, all of that will come to your mind in the subsequent lectures. But then there's also the idea of applications. So we talked a little bit about physical sciences, the CFD special that we will have to this year in the course for you. Also thinking about more numerical methods and, based on physical laws where HPC has lots of applications with, but more recently we also changed the course and topics again and again based on requirements we get from students, based on students' feedback, but also on the YouTube community and also industry that looks our lectures. So we integrated some more aspects of AI because basically HPC systems are also more and more used with AI. And we clarified a little bit that AI means basically deep learning, and there will be also lectures on distributed deep learning, leveraging multiple nodes, and with this also multiple GPUs. Hence, the course blends in, let's say, lots of different ideas. We cannot cover the whole HPC domain. I also was alluding to the Euro HPC Master in HPC if you're interested to learn much more that is existing today. So one course cannot possibly cover everything from HPC, but we try to make it as interesting as possible to learn about the different facets, starting from parallel programming with MPI and OpenMP and distributed memory and shared memory, up to GPU programming using AI, and then, tuning AI models even with hyperparameter optimization and AutoML techniques. As a special this year, we have also Reza, my co-teacher, that will also be part of the second part now of the prologue, discussing with you a little bit more the detailed course outline. So we talked a little bit in the outline at the beginning of the prologue part 1, but now also we want to have some substance behind it. So what you can expect from these, let's say, different lecture types. So before I start, however, let me tell you that this course has been grown since quite a while now. So you see it dates back here to 2017, 2019 in the in the versions that we have roughly today, but we always basically were updating several lectures. We changing the course depending on, let's say, more frequent aspects like we have now with distributed deep learning or hyperparameter optimization AutoML techniques. You see also in previous parts like 2017, we had much more applications, terrestrial systems, systems biology, and so forth. So I encourage you also to look at the old resources if you want to learn more about high performance computing. And in order to get a better understanding now what all the different lectures entail when you enroll in the course, I would like to go now lecture by lecture, and I will do this from lecture 1 to lecture 7. Bear in mind that there will be practical lectures also alongside those. So we put here the emphasis on the conceptual lecture parts in a sense, but as you understand from the green that we had in the beginning, when we talked about the structure, there will be practical lectures alongside each, in this initial parts and also in Reza's part. So lecture 1, high performance computing, as the name suggests, is rather an introduction lecture. So what actually means high performance? You must have many questions. So what are the basic building blocks that you can see in HPC? What is the top 500? What makes really a supercomputer in HPC machine? Why is parallel computing? Let it be shared memory or distributed memory or even GPUs with high throughput ideas today. What is the idea of parallelization and so on will be a little bit closer before we then go later on to the parallelization techniques with MPI, doing this on distributed memory that you see here essentially, where you need explicit message passing or you have shared memory with OpenMP, having the opportunity really to address the same shared memory space. So memory is another part of HPC architecture which is important. not only CPUs, GPUs, and the strengths of the CPU is important. So all of that counts in, like the interconnect as well. Especially if I send, let's say, many of these messages in physical applications like weather prediction, you can imagine that the interconnect also matters. Hence, we talk about HPC architectures driven by co-design needs of applications, of parallel applications in physical sciences, but also integrate a little bit of AI, as I was alluding to at the beginning. These are also having here and there similar structures. Also reusing MPI, what we will see how that materializes in lecture 7. Now, the HPC ecosystem is equally important because the ecosystem as such is the way how to use one HPC system or many, right? So there's a software environment, meaning there's SSH access, there's schedulers, there's a Unix derivative, usually as operating system. So all of that is not like what you know maybe just from Java, and there will be somewhere a kind of kind of visual system allowing the programming of it. So here we talk about low-level access, SSH access, and also here and there we make the case then of C programs during the first couple of course parts, also to get you closer to MPI and OpenMP and programming. But we, as I said earlier, also we will keep this programming of a moderate degree. And then on the, let's say, more broader, let's say, view of the course, we would also, of course, go to a little bit of the EuroHPC joint undertaking. What is the ecosystem at the larger scale? What are the supercomputers that are in high performance computing within Europe and that can give you resources once you are in a company or in another research lab? So this is also important to target. Finally, just a couple of pointers really to the quantum computing systems that are emerging under the umbrella of high performance computing as well. A new form of computing, but that is also considered to be one of the sort of special accelerators we have in computing today. Hence, it makes sense to integrate them in HPC systems. So lecture 2 will be much more practical. We will be, doing things which you also will do in your first assignment, programming in parallel. This will be still, let's say, smaller projects, smaller ideas, so you will not have the big, bold C programming to do, but rather understanding distributed memory. Why is message passing so important? Because I cannot address the address space of another processor. It's really distributed, as the name suggests. So there will be different standards we will look at, and one of the most important will be the MPI, the message passing interface concept. And also there's not only a send and receive pattern that this graphic here suggests between the different processors, they're also collective that you see here, a broadcast from one processor to all the others, sharing data across a HPC machine. So then we will start there and also with some parallel programming practicals in diving into parallel programming with C using MPI, where libraries, modules available on this HPC system will be important to understand. So which compilers are there? Then a little bit of thinking in parallel is also something which we will tackle. So what are the basic building blocks of an MPI program? What is the MPI runtime and why we can basically program these days MPI applications not knowing how many CPUs we really get. So there's some bad coding examples versus good coding examples. Then, after having started with the practical so that you can soon start your assignments, we will have a deeper look into parallelization fundamentals. And this topic is loaded. Understanding load imbalance, understanding the idea of what you see here, for instance, as a max of an array, to do this in parallel. So how we jump down basically a big problem into little pieces. There's also different communicator techniques in MPI, like the Cartesian communicator, that is quite useful in order to enable this domain decomposition, different ranks, different ideas how to use this Cartesian communicator. And we will talk about this when we talk about parallel applications. There's also some, let's say, important strategies for parallelization that you should know. Not only the reasons why you should do it, also limits like Moore's law, and then also perhaps later Amdahl's law that brings us really into theory and some terms. So the idea there is to understand a bit load imbalance, speed up, why basically the scalability of a program is always limited in their serial parts. There will be some scalability metrics in performance, but in the end, still the theory will be not so intensive. So don't worry about this. It's much more to understand a little bit about the parallelization aspects here in the course. Then coming back to the practicals, one part of the assignment will be OpenMP. And here we go to shared memory programming. So that means that instead of processors, we have different threads that can all address the same shared memory space. So the, let's say, scalability is sort of limited. You have to have shared memory. Hence, we will also look a little bit on how to program in hybrid and parallel, meaning combining shared memory with distributed memory. We don't do that too much in the course, given new topics like deep learning and hyperparameter optimization and so on. But this is, of course, the way how you really go big. But with OpenMP, the focus first would be on so-called Sentinel with pragma statements that you see here to do something in parallel just by essentially marking parallel regions. And this is an interesting, different concept than we have seen before with MPI, doing explicit message exchanges between the different processes, because here everybody has access to the same variables in the shared memory. So by doing this, there's sort of different, let's say, building blocks also for OpenMP and shared memory programming. We should talk about why it is so easy in a way to do parallelization on loops, still to have a look on local and shared variables, why it is important to have sometimes critical regions so that not we have a lost update or of a variable, or that there are race conditions we have to think about, synchronization as such. And of course, we always will differentiate it with MPI, which is another, let's say, parallel programming paradigm. Alongside will be always applications. That is basically true for almost all lectures here, bringing us also to lecture 5. So lecture 5 is on accelerators and graphical processing units. And this is something that when I would be standing in class would ask you to raise your hand who knows about GPUs, and the most will answer, yes, I know them from gaming. I have them somewhere in some desktop machine doing beautiful graphics for my games. But here we talk about a special breed of GPUs called GPGPUs, which are much more for general purpose processing. Right, so the concept of GPUs is very good, enables quite nice scalability, and we will talk about why this is so interesting. You see the color coding here, how you can actually chop down big matrix vector multiplications or matrix multiplications according to mathematical rules quite nicely on GPUs, and that makes really a big difference if you now think about deep learning. I will talk about later. So with this, we also think about different architectures. What is the difference between a so-called many-core that we have in GPUs to multi-core? So essentially saying there's a moderate, powerful processors, but very thousands of them compared to, let's say, processors with single-thread performance or high single-thread performance that we have in multi-core. So there are differences, although they're all CPUs and GPUs at some point in time. And then we have, of course, different architectures, Kepler, Pascal, Volta, Ampere, and now we have even Grace hoppers in NVIDIA. But we not only look at NVIDIA, there will be also GPUs from other vendors, which is important in this particular lecture. Of course, some GPU applications will stimulate already the uptake in the scientific community on simulation sciences libraries, but also more dominantly in the machine and deep learning. Hence, what's next? Introduction to deep learning. And this by far is not what the name suggests. So this is rather really one lecture in a HPC course giving you all the foundations of artificial neural networks very quickly, giving you an idea what deep learning is and mostly why it is so computational complex. And there we talk about lots of matrix multiplications, matrix vector multiplications, depending on your architecture. We will talk about this and how this alludes to many parameters to learn. And the more bigger and bolder the deep learning architecture, the more HPC is required. Hence, we talk about some of these models, like convolutional neural network, long short-term memory for time series, others are for images, And we will also talk about the HPC advantage a little bit of training these deep learning models, essentially from the basics. But then lecture 7 really goes into much more detail on why HPC is then really, really important. And you see that a little bit here when you think about these different HPC systems, Jubels, Jureka, that are existing, and how basically by adding more and more nodes, we can have really a speed up with distributed deep learning enormously when using cutting edge, let's say, neural network, or more notably deep learning architectures. You see a residual network used in one of our papers by using really high performance distributed deep learning techniques. Now, the devil is in the detail. You can do this with different concepts. So often the concept of data parallelism is used. You see that a little bit here. There's a data and the training is done on the same model, actually, on different nodes. And then there's a message exchange at some point in time, having the learning, the gradients. We will talk about this in lecture 6 and lecture 7, what gradients mean, which is essentially the learning taking place. Then distributing this with all the other, let's say, training processes to improve the model. So over time, you can come then to this kind of idea of speeding up the training while still keeping the accuracy, which is also, of course, very important for us, or a low error rate. Now, other model ideas is pipelining, model parallelism. We will talk about this briefly as well as covering different tools in lecture 7, which are TensorFlow, PyTorch, HoloBot, which are commonly used for it. We do lots of research in remote sensing using this parallel and scalable deep learning. Hence, there will be some applications around this that really leverages multi-node training on HPC system, like you see here, in order to get a significant speed up of the whole training time. Usually the inference, once you trained and you have the model, and then using it for a particular classification task, is very quick. So we talk about this in inference, no training necessary anymore. The model is already trained. Then GPUs are still good, but not so necessary as training. And we will talk about this also in this particular lecture. And I think now I would like to leave the table for Reza to contribute and start with lecture 8.
Hello everyone, thank you Maurice. I'm Reza. Currently I'm a postdoctoral researcher at the University of Iceland working with Maurice Research Group. My interest area is computational fluid dynamics and my focus on the turbulent flow. I am using the machine learning and deep learning and HPC and the CFD to understand complexity of the turbulent flow, which is an unsolved problem in the physics. I will take over the second part of this course from lecture 8, and it's my pleasure to be in this course this year also. Let's go back to the lectures and we can have overview on them. In lecture 8, we will have introduction on the computational fluid dynamics. It's called CFD. In the fluid dynamic area, the most of the problems in the real world don't have analytical solution. So we are using the numerical approaches from the computational of the CFD and dealing with this type of the problems. From the other side, CFD for most real problem, it's required high computation. Most of the problem are required to have access to supercomputers. So that's why the HPC is the key player in the CFD application in the industry. The CFD is broad area. However, in this lecture, we will have a short background and we'll talk about the range of the application, about the Navier-Stokes equation, which is one of the fundamental concept in the fluid dynamics. We will talk about the different schemes it's used in the fluid dynamic. Also, we will talk about the classification of flow. In the fluid dynamic, we have two main regimes of the flow, laminar and turbulent, and most of the flow are turbulent. As I mentioned in the beginning, the turbulent flow is an unsolved problem in the physics, and that's why the CFD could help us to understand this complex phenomenon. We will talk about the solution methods in the CFD when we're creating the algebraic equation and how we can solve them. Also, we will talk about the meshing, how we make the composition of the domain of the problem, and how we are using this approach in different softwares. We will have some tips about the boundary condition and its effect on the CFD problems. Then we will have overview on the three main categories of the CFD used in the turbulent flow: Reynolds average Navier-Stokes arrays, large eddy simulation LES, and direct numerical simulation DNS. We will talk about the accuracy of this method, about the limits, and how we can use them for different type of the problems. And we will have some example to make a comparison of the accuracy of these different categories. Then we will move on to lecture 9, which is present the parallel computing for the CFD. Since in the lecture 8 we will talk about the CFD and how it's required computation. Then in the lecture 9 we will show how the parallel computing could work for the CFD domain. Since we have a domain of the CFD, we need to make a decomposition, and then we need to use a different topology to solve this kind of the problem. We will talk about them. We will have an introduction about the vector computer, superscalar computers, and how parallel programming working. Also, we will mention the explicit and implicit methods in the CFD, and why for the implicit, for example, we can work with the parallel computing to present the accurate solution for us. Then we will present some example of the structured explicit, unstructured explicit, and the iterative schemes for parallel computing. And as you can see in this slide, we are presenting the structured and unstructured meshes, which is dependent on the type of the problem and the accuracy which is needed. In lecture 10, we will have an example of the OpenFoam software. OpenFoam is open source software, and it's used broadly in the CFD, especially for the research, and also in some kind of the industry. Since it's open source, so it's make it easier to make geometry for different type of the problem. And how we can make the meshing, modifying the boundary condition and using the relevant solver. We will discuss how the laminar and turbulent flow could be simulated in the OpenFoam, and we will run example on the OpenFoam. However, the first example will be small, which could be run on the single computer, and then we will move to see how we can run the OpenFoam on the parallel computing. We will present the decomposition approach in the OpenFoam, how it works and how we can decompose the domain of the problem, and run the simulation, and then collect the target properties in the problem in the end, and we can visualize the solution of the OpenFoam. Here you can see beautiful of the visualization of the OpenFoam application. So this is a great capability that we can use the OpenFoam and present this solution. Then we will continue to lecture 11 regarding the deep sequential models and their application in the CFD. As we mentioned, in the fluid dynamics, most of the flow is turbulence, and turbulence is unsolved problem. In recent years, since deep learning and artificial intelligence developing in many areas, there is a lot of interest of this capability to be used in the fluid dynamics, especially in the turbulent flow. One of the approaches is making prediction for some properties. For example, when we have a flow with turbulent regime, we can have some data to train the deep learning and make a prediction of that data with specific properties like the pressure, velocity, or temperature. In this regard, we will present one of our research which use the turbulent flow data with long short-term memory and gated recurrent unit to predict the velocity of the turbulent flow which doesn't has a known pattern. And we will talk about the design of the model and how get training of this model. We will present the comparison of the LSTM and Go of this model, and it will be a practical course with running this model, and we will see how the HPC is required in this type of the application, which combined of the artificial intelligence, CFD, experimental data, and high performance computing. In the next lecture, which is lecture 12, we will have an introduction for the Lattice Boltzmann. It's an approach which could be alternative for traditional of the CFD method, which is working with a algebraic equation. In the Lattice Boltzmann, it's basically working with the streaming and collision of the particles. We will talk about the history and the concept of this approach and the Boltzmann equation. Then we will see the boundary condition, how it's working here. We will present the advantage and disadvantage of this approach and what are the limits. For example, in the turbulence flow, we need to use some tips to run the Lattice Boltzmann based off the problems. We will explain the terms of the Boltzmann equation and how we can use it for different problems. There is a methodology to model the problems with the Lattice Boltzmann, which is usually work with particle tracking. Also, we'll present some example from the Lattice Boltzmann for turbulent flow, and also how the Lattice Boltzmann based off the large eddy simulation. In fact, Lattice Boltzmann has a great capability to be used with parallel computing, and we will discuss this matter, which is a great advantage of this approach in the CFD. In lecture 13, we will present example of the deep learning in the CFD from the attention mechanism transformer. Basically, this model working with encoder and decoder architecture and the self-attention and positional encoding. It's a great capability of these models. We will talk about these great advantage, and also in the beginning we will have introduction about how this mechanism is relevant to the cues of the human body, and how it's led to this approach. We will talk about the transformer architecture and how we can use it for the CFD. Then we will see practical example for data set from the turbulent flow. As we said, it's complex and doesn't has known pattern. So we'll present it practically. We train the model with the data and then make a prediction for the velocity of the turbulent flow, then make a comparison with some other models like LSTM and GRU, which previously used in our research, and it will present great validation of this approach. And this approach presenting a really good ability of the transformer to be used, since a transformer working with the encoder and decoder, it seems regarding the parallel computing work has a good performance, and make it possible to have efficient high performance computing with these models for the turbulent flow. Then we will continue in the lecture 14, which is will be a new topic in this course this year, hyperparameter optimization and AutoML. We will have invited lecturer Marcel Arf from our research group at the Jülich supercomputer in Germany, and this lecture will present the hyperparameter optimization. The hyperparameters are affecting the performance of the deep learning model, and they are very important to get the accuracy of the prediction, for example, in the deep learning model, and we can control the error rate. However, most in the traditional approach, the hyperparameter usually used by the experts, and we can say in some way they are a trial and error. But in these days, there are tools that could be used to make hyperparameter optimization and optimize the model, like Raytheon. And in this lecture, it will be presented. So these toolset will help us to find the hyperparameters in the better way and make the model much more efficient. Also in the part of this lecture will be presentation of the AutoML techniques. Usually, as we know, for a specific problem, we are using one model when we are designing it, and we see how it's working. But automated machine learning helping to make a combination maybe with different model and find the best one. So we can have best performance in the practice. One of the another goal of the automated machine learning, sometimes the user of the deep learning maybe doesn't need to be expert in the machine learning, and these system toolsets helping this kind of the researcher to use the capability of the machine learning. The example will be from the AutoGloon toolset to presenting this capability of the AutoML. Then in lecture 15, we will present the green energy and HPC application. This lecture will present two perspectives of the energy resources. First one, it's in the green energy, the idea in the most development countries and cities to have smart cities, which is required to have a smart power grid. When we are looking to power resources in this kind of the power grid, which could be from the wind energy, hydropower, or solar energy, and some other new idea like the hydrogen. It could be one idea to use the deep learning and machine learning in this area to have a prediction for the power production, which currently has a lot of interest in this area. So when we are talking about the deep learning and large data, HPC is the main player to make a prediction of this type of the power production. to be able to have a forecasting of the production and make the power grid smart in the smart cities. From the other perspective, the HPC have a power demand, and it's very important to be able supply this demand from the green energy, which make the computation supplied from the green and clean and renewable energy resources. We will present some computation calculation of the demand of the HPC system and how a renewable energy option could make these supply from the green energy. Here I ended the overview of the lecture 8 to 15, and I'll leave the rest for Maurice. Thank you so much.
So thank you very much, Reza, for these interesting lectures of the course. Computational fluid dynamics, very interesting topics, blended also with artificial intelligence these days, not only based on physical laws. Very interesting and also timely topics. We hope we provide you as students, including also, of course, some green energy considerations. Let me just close with a couple of elements here, especially final lecture 16, what you can expect from the epilogue. That is rather an informal final lecture at the end in April, where we can answer remaining questions, also think about further studying topics that might be useful, going deeper in AI, going deeper in HPC, and so on. Then, of course, the course projects we had together that we will also talk to you with more in the next couple of weeks. We will have lessons learned, debrief them together, a summary. Everybody of you have to have a short presentation and so on. And the idea is of this lecture 16 is really thinking from the course materials from a different perspective. So really mindset, skill set, tool set level. So what are potential job offers? Where can I go? What I have learned, what I want to do, how I can use the know-how really now in job offerings. But then also the skill sets, so reviewing some of the different, let's say, elements that stand the test of time. So parallel computing methods, HPC versus HTC, programming skills, MPI, OpenMP, GPU programming. And then, of course, also thinking how I can put the skill set maybe into PhD positions or even do a master thesis project with us in HPC. And finally, on the toolset level, of course, we have also now gained at this lecture 16 and throughout the course a significant insight in different tools and scientific computing libraries. We want to find them again in job descriptions, but also understand how I can employ them maybe with other parts of courses. And of course, then reveal a little bit from the toolset perspective what could be future topics again. So quantum computing is around. It's a little bit different to program. Neural networks on the chip, neuromorphic computing. These are all different tool sets in modular supercomputing, which are very close to this content of the lectures. And with this, we covered all the course lectures per se. As an appetizer, which is a bit maybe also a funny perspective of the course, I want to close today with the high performance computing in the view of DreamWorks. So the penguins of Madagascar, I hope you know them. This is a quite nice video, but it captures nicely the essence in a way that everybody can understand why high performance computing is necessary. So just at the end of each lecture, as I said to you, there's a lecture bibliography, usually with all the references you can find from my part, but also here you see Reza's bibliography, which has basically the same numbers. We didn't manage to join that completely, but I think you can see from Reza's part what are the corresponding bibliography elements. And then finally, acknowledgements in each of my courses, of course, given the fact that as professor, you rely really on PhDs, working with them together on doing many of the aspects actually you have seen here in part of the course and that you will see as part of the course. And in this sense, it's also good to credit them also very highly in this course. And I stop now the recording and would say we see us the next time with the next lecture. So see you next time.